Hello explorers, and welcome back to another Convolution neural net episode. And I thought we should do a little bit of a catch-up and talk a little bit about where I'm at the moment. I have done a lot of translation and have pretty much most of the structure done. So I think the next part of my project is to actually debug and get it working, and then try to rebuild some stuff that might be a bit confusing when you look at it. For most of these components that we use and layers that we use are quite easy. They don't have that much logic in them, so you should be able to write them in a very concise and describable way. Maybe it's because of JavaScript that you like to keep it concise, so it's easier to minimize or something. But in my case, I think they have been a bit coarse with their naming of stuff, so you can't really follow along, and I don't like that. I like more of a broader namespace that you really describe every element and so on. So just start with what I've added so far. We have this project structure over here. It's a little bit small, so I don't know if you can read it. At the moment I have a few data objects. I have a back propagation result, a data block, and an output definition, and also training result. Output definition might not be the right word for it. Might change that to a definition later on. The data block is the actual work unit that we send through the network. The output definition is used when you set up the network to give the next layer its input data for the size of the current working data. And back propagation result, it's for the back propagation as it sounds. You get a result for each backward loop, and that is summed up and put in the back propagation result and sent back. And so then you have the training data, which is the actual result of a training data run. So we can look at those individually later on if we have the time, but those objects are objects that I have discovered during the implementation of the different layers. So those are more of my design. Of course, when I had data to go with, I used the same variables so I could easily see where they came from. And then we have all the layers that we already talked about. I have added a MIST reader to read the MINST data, this numeric data set. We have an ADA grade trainer that in the old JavaScript library you have a trainer library and a lot of training methods in each of those. I wanted more to have one trainer per class and then have an interface that every trainer implements. And then we have our network and our test case. So the class I have open here, the MINST reader, it just reads the MINST data, and the interesting thing is read next label and also read next image, which gives you a number of bytes, which is the 28 times 28 number of bytes in the raw data from the file. So that's the way we get our input data to our network. So let's look at some things that I have translated. If we go for this, we can start at the data block. In the old implementation, this was called volume. So we have the new implementation over here and the old implementation here. And in this volume, we had a few things to set up the object, which were dependent on the different input data. And then we have a get, set, add, get grad, set grad, add grad. We have some cloning information. We have some add from and set constant. We changed the whole weights metric to one value. And then we have some JSON, functions to go from data to JSON and back. These functions I have skipped over so far. So if we look at my implementation, I have discovered that I need the size of this data block and the depth. And then I need to arrays that I work with, one with weights, and I kept that naming. I might change that later on, and one for the gradients weights. So, and I kept that name as well. And then we have this data block initialization, where we initialize the two weights, the weights matrices, and then we fill them either with the value that we give or with a random value for the weights, and the gradients always gets filled with zeros. And that's pretty much what we see up over here as well, but in JavaScript coding instead. And then I have this function to add my image data. I thought that it was easier to put in a byte array of image data into this. So that's how I actually propagate my image data. So I put it into the first block and then I let it run through the network. And then I have some helper functions to get the size of this data block, because those are needed in the different functions. Then the getters, I changed those so you actually can get a weight on a specific index if you calculate the index in advanced, and you can get a weight at a specific position in the matrix dependent on x, y, and depth. And then you can set the same information either by the index or the position. So these getters and setters are equal. And then we have an add weight that we don't use at the moment. So I think these gray things in IntelliJ is quite nice, that you get a visual representation that this is never used. You have added a function that is not needed at the moment. And because I haven't implemented all the different layers and all the different functions in this JavaScript library, I don't know if I need it in the future, so I will keep it at the moment. And then we have the gradient getters and setters, and those are quite similar. And I changed the name, so I have get gradient and set gradient and so on. And then we have clone and zero, and that's pretty much just create a new data block with the current sizing information and just set every value to 0. And then we have a full clone, and then that does the same, but it also transfers the weight values to the new data block. So the gradient isn't transferred, but the data in the weights are. And that's pretty much what's done in this function. And then we have clear gradients. That was a function that I thought were nice to have, because in many situations you have functions in the different layers that actually clears the gradients at different intervals, and they actually do it by pointing directly to the array. So I created a function for that. And then we have functions to get the full weights and full gradients, because some functions needed that to work well. And then we have the 3 functions: add from scaled, and const. never used at the moment, but I implemented them anyway in case that I needed them in the later stages. So that's that. So let's look at a simple layer then. We can start. I thought that I opened the first layer. I didn't, so let me just open the input layer as well. So here we have the input layer, and that should be in the layers input class, and it's very simple. In this case, you don't know if you have any definition with output, so it just sets the different values into this class, and all the out information in each of these layers are transferred to in values on the definition in the next layer. So to do this, I actually created this out definition def, and I put those values into this definition so I can pull them out in the next class over. And then we have forward, which is pretty much just setting the value and returning the current data block, and backward propagation does nothing, and also this params and grams that I changed to get back propagation result, because I thought that was a better name for that function. So that's the input layer. So now we can close that out and concentrate on something else. So let's go in and look at the next layer up, which should be convolution. Didn't I open that either? I was sloppy when I opened stuff here. Let's see that we actually have everything opened. And convolution layer. So this is pretty much a little bit more involved. So see, we open it up here. It's in the dot products. So the convolution layer. Here we have a lot of different values that are needed. We have some decay multipliers. We have the data blocks for in and out. We have a bias. We have some sizing information, both in and out. We have some other sizing information, and we have a stride and padding. I think the sizing information is for the filter, and stride and padding so as well. And then we have the array or list of data blocks that actually has all the filters, and we have a data block with the biases. And then we go through and initialize everything here. We calculate the new output from the different values of the filters, because each of these filters will create a new layer with a new size, dependent on how large a filter you choose, how much padding you have in stride. The output array will differ a bit. So this is that calculation, and if we look here, I have just transferred that calculation over with the same names and everything. This layer type for me is not interesting because every class has the specific name, so I can just look if it's an instance of a specific class, then I know it's that kind of a layer. So I didn't bother with actually setting a type. And then we have the bias. If we have any input bias, I just use this bias def value that I have up here. And biases is a new array as well, which I create down here, and it doesn't have any bulk. It's just the output depth. So you have one value per depth, so per filter, that is. And then we set the current output information so we can use it in the next layer up. And the forward is also translated directly from this function. You can pretty much read it. The first point here that I set inact from this volume, I don't use that value either in the back propagation or in this function, so I never set it. And I believe so, at least. Let's see here, because I have it up here, right? No, I set it up there. Okay, I didn't see it. I use it. Yep. So my bad. I didn't see it. But in this this function, we create a new block with the sizing information of out, and we set the different values of the filter, and then we go through and calculate the new value. So everything here should just be the same information. The only difference is that I have added types and changed the different name somewhat. Padding was pad before, so you see here pad and so on. But I don't like that you just create shorter names for things. That when pad, well, it explains something, but I think padding is a better name for that. And I will do more of that work later on when I get this working, because I haven't run a full test of this yet. So yeah, this calculates the weight by taking the filter weight and calculate it against the position of the current data block. And then we get a value that we add, and we use some biases and add those as well, and then we set new weight for the output. So that's pretty easy to understand in broad strokes. Backward propagation did the same with that one. Pretty much just kept the names, added types, and as you see up here, we actually do this zero out of all the gradients. But I wanted to use a function to make that more clear. I think that's a clearer way to describe it, at least. And here you see I use these functions instead of looking directly into the object and making those public. And yeah, that's pretty much it. Here we see how I use the add gradient function instead of just this plus operator on the raw value. I also think that's a bit nicer to keep it separated. And the same with biases down here. And the result function, here I create a result array, and I go through all the filters, and for each filter I get the weights and the gradients for the filters, and just add the multipliers that I have calculated in this layer to that result. And then lastly I add the biases, weights and gradients as well, with no decay. And that's pretty much what this function over here does. So that should be the convolution layer, and that's the most intricate layer of them all, I should say. The other layers are much smaller and easier to understand. So let's go for this is another thing that I saw, that all the layers that are lost in the operation, we do some different calculation with those, and we also do a different step in the back propagation of those. So to separate those out a bit and give those a little bit more of a definition, I actually created a layer that I called loss layer, where I have this backward function that you could give a y value, and this y value is the actual prediction or the actual correct value. So when you training the network, you will give this layer the answer. So that's this y value, and then I needed a way to get the the output act as well from the loss layer in the back propagation. So this is that interface for doing that. And I think the softmax is the only loss layer. That's the loss layer in my network. It has some values here that I implement from the beginning. We have the output from the softmax and number of classes. So that's how many number of inputs. Why do I have a number of classes when I don't use those? That's interesting. Let's look at this information here. We have number of inputs. That's calculated, and then we set a depth for the output to number of inputs. That's interesting. So the previous layer gives us how many classifiers we have. That's a bit weird, isn't it? I thought that this layer should actually have a depth of the number of classes that we'd want. But we can look at that later. This might be something that I want to change, because I think that's a bit strange. And why will we... you actually could give the definition number of classes. That's because I have added that here because of that. So why it's not used, that's a bit curious. And this softmax layer, if we look at the forward function, again we create the new data block up here. We get all the weights. We get the first weight and set that as our a max value, and then we go through all the values in the weights and try to find the largest a max here, and then we so that's the largest weight that we find in our data block going into this function. And see here, compute exponentials carefully, do not blow up. What a very insightful comment they have put here. So I create this layer with outputs. I fill it with zeros. I have this sum value, and I go through and find the sum value for... Okay, so I look for the differences or distances from this max value, I guess. Don't really understand this function. Math. And we'll look into that more later on and make that more understandable. We compute exponentials, okay? And then we normalize the output to all sum to 1. That's so we actually get the value. Let's say that we have one value that is 80% right, and then two other values that are 10% right. So we want all the values that we have in our array to sum up to 1. So we can say how confident we are that one of the values are correct. And then we save the information for the backpropagation. And here we see this specific function for backpropagation for this layer, the loss layer. And this backpropagation is a bit different. It takes an actual correct value. We set the data block, clear the gradients, go through and add new gradients with this simple function where we go through all of the values in the depth. If the current value is right, then the indicator will become 1. Otherwise it becomes 0. So that's pretty easy. And then we look how far this indicator is from the current value. So this is the current guessed value, and we will then say how far from it is, and then we will add that as a gradient so we can use that in our backpropagation. And then we calculate all the losses with this function down here. Loss is class negative log likelihood. Also a very strange comment. And we don't need any backpropagation result, because the only thing that we are interested in is the actual loss, and we want to minimize that in our function. So that was the softmax layer. Let's see here. Close these up. Fully connected should be over here. Oh, it doesn't want to. I think I need to take a little break here because my throat is a bit sore, but I'll see you in the next video.